All right, so for the next section, I want to go over 1.5 limits in continuity. And if I had to pick one section out of all of the ones for the first unit, I would say that this is by far the most important one. The AP exam loves asking questions about continuity, whether it's for a free response question or a multiple choice question. All right, so how do you determine if a function is continuous at a specific point? So a lot of times they'll ask you to look at a specific x value and determine if at this x value it's continuous, that the function is continuous. So there are three conditions for that, and for our x value, we're just going to use c right now. All right. So three conditions to determine if it's continuous at x equals c. The first thing, it has to be defined at x equals c. All right. And if you're looking at this graphically, you'll know it's defined if it has a closed circle. Okay. If it has an open circle, that means it's kind of undefined at that point. The second condition is that at the limit as x approaches c for f of x has to exist. Okay. Now, if you guys remember from section 1, how do you determine if the limit as x approaches c exists? Well, again, if they don't indicate a sign like positive or negative or coming to the left or coming from the right, that means that as it comes from the left and as it comes from the right, it has to be the same value. So that's how you know if it exists at that as the limit I'm jumbling up my words. It exists if the limit as x approaches c for that function is the same value coming from the left and coming from the right. All right. The third condition that has to happen is that the limit as x approaches c, once we establish that this exists, it has to equal the same closed circle as f of a, or f of c, sorry. Okay. So once you establish that this exists, if this value is the same as f of c, then condition 3 is met. Okay. And the way that we're going to address those problems, and we're going to do a little bit more, like we're going to get into some other things first, but when we actually do these problems, you'll see that there's like 3 bullet points I want you to do every time I want you to prove continuity. So, but before we get into that, I kind of want to show you guys graphically what we're dealing with. So they're saying at x equals c, at each of these following x values, I want you to tell me if it's continuous or not. This is probably something I would have you do on your own or during a bell work assignment, but since we don't have that luxury, we're just going to go ahead and do that here. So at x equals 9, so let's look at 9. Is it continuous at x equals 9? Well, it's not, right? Because here's the thing. It's defined at 9, so the first condition is met, but the second condition is not met because as you approach it from the left, you reach here, but there's really nothing to approach it to the right from. So therefore, it doesn't really exist there, okay? At x equals 4, right? That is definitely no, because first of all, there's no value that exists at x equals 4 because it's an asymptote. At x equals 3, again, it's kind of the same situation as what we had before. It's approaching something from the left, right? But from the right, it's not really approaching anything. Yes, it's defined, but it has to meet all 3 of those conditions, right? Now, if they had something else instead, like maybe let's go back to x equals 9. Maybe if this was like an arrow going forever this way, this is when we can say it's actually continuous. And a good way that I like to tell kids to think about continuity is if I were to get my pen and drag it along the graph, if I never have to lift my pen at any point, then it's continuous for as long as I have like my pen running through it. Okay. Like say, for example, like see how over here, if I start my pen over here and I drag it along, notice how once I reach this point, I have to lift my pen and come over here and to continue the function. Or even if I have to lift my pen over the hole to continue the function, that's how you know if something is not continuous. All right. So let's look at x equals 0. So at x equals 0 at this point, well, it is defined. Pretty much there is no open circle there. As you approach from the left and from the right, it lands in the same place. And it lands at that same place where the closed circle is. We're good to go. So that's a yes. All right. And then at x equals -3, nope, it is not. It is not. That's not the case because sure, at x equals -3, it is defined, right? The limit does exist because as you approach it from the left and right, it does get to the same place. However, the limit at x equals -3 and the where it's defined is not in the same place. So condition 3 is not met. Okay, and then at x equals -5, well, again, this is definitely, I mean, you could just visually see it's not continuous because you have to make a jump from here to there. So no. All right. Now, if you continue on to the notes, I went ahead and kind of gave you guys just sort of an overview of the different forms of discontinuities. All right. So let's see. So these are the types of discontinuities that you'll see. You'll see removable or point like discontinuities, which are, we're used to calling them holes. So if there's a hole at x equals 1 or here at x equals 1, it is not continuous at x equals 1. It's continuous everywhere else, but at x equals 1, it is definitely not continuous. This is called a jump discontinuity. So if there's a jump discontinuity, that means that the graph kind of goes on over here, but then it kind of jumps to a different place at that x value. So that's a jump discontinuity. And then, of course, we have asymptotes. When you see any sort of asymptotes, then it's obviously not going to be continuous because you're kind of stopped by that asymptote. All right, so those are the different kinds of discontinuities that you would have for this section. All right, so on the next page, they want you to find the points or intervals at which the function below in this graph is continuous, and the points at which the function is discontinuous between -5, so from here, to +1. I meant to say 10. Sorry, to +10. Okay. So again, if you guys don't remember from pre-calculus, if they say like from between which intervals is it continuous, well, you're gonna have to use like either parentheses or brackets depending on whatever part of the graph you're looking at. So over here, it's pretty much continuous from -5 up until we reach -3, not including it. So from -5 to -3, not including it. And then if we want to like describe another portion and kind of continue this on, we say also from -3, not including it, until it's pretty much continuous, like from -3 all the way until we get into +3, right? So it's continuous throughout this whole portion. And then it takes a break, so we're going to take a break here. And then it's going to continue from +3, not including it, all the way until +5. Then it's going to take a little break with this hole, and then it's going to be continuous from +5 until +7. Then it's going to take another little break, and then it's going to continue on over here from +5 up until infinity. Or, well, let's just say 10, because that was where they wanted us to stop. Okay? So those are all the areas in which it's continuous, and again, it's important for you to recognize when when you are going to have a little break or when you are lifting your pen, kind of like what I was describing earlier. So if we went ahead and described the discontinuities, okay. So there are quite a few discontinuities here. First of all, if you look at x equals -3. You have a discontinuity there, and essentially you have a hole or removable discontinuity. All right. If you look at x equals +3, you have another discontinuity there, because right there you can kind of tell that there is an asymptote. So we have a vertical asymptote there. All right. And then over here at +5, again, we have another hole, removable discontinuity. Okay. And then on x equals 7, we have a jump discontinuity. All right. They're not going to like ask you if you can identify these things, but it's important to kind of understand your vocabulary and understand what makes something discontinuous. Okay, now this is the real meat and potatoes of this whole section. This is gonna take probably the majority of the video because I really want to make sure that you guys do this. This is a very important question for a free response on the AP exam. So It says using the graph above, determine if the function is continuous at x equals -3, x equals 3, and x equals 7. So again, we're going to have to do all three of the conditions for this, all three of the conditions for this, and all three of the conditions for this. So I'm going to start off with x equals -3. Okay? So again, the first condition was that, let's start with the second condition. The second condition is that the limit has to exist. So we're gonna do three things with all of these problems. You can almost think of this as like bullet points. So the first thing you're gonna do is you're gonna take the limit as x approaches this value from the left, right? So when we do that, as x approaches -3 from the left, it is +1. No, sorry, -1. What the heck am I saying? All right. Then we're going to do the limit as x approaches -3 from the right. So as you come from the right, it is also -1. Okay, so those are the first two things you do. Take the limit as it approaches that x value from the left, the limit as it approaches that x value from the right, and then the last thing you do is you take f of that x value. So f of -3, what's the value that it's defined at? It's defined at +2. All right. So again, once you do these three things, you can go ahead and decide and justify whether or not the function is continuous at that point. So then over here, in order for the function to be continuous, all of these values have to equal each other. So I'm going to say, since the limit as x approaches -3 of f of x, right? And I'm not going to use the symbol as if to say like, these two are the same. This does not equal f of -3. I'll just say f of x is not continuous at x equals -3. All right? This is how you would answer that for your response question. You have to do each of these pieces. Once you miss one of those pieces, good luck trying to get full credit on this. All right, so then I'm going to go ahead and do x equals 3. And again, I'm going to start off by taking the limit as x approaches +3 from the left. Right, so when I do that, I get, so as +3 from the left, it's equal to infinity. Then I'm also going to do the limit as x approaches +3 from the right of f of x. Again, that's also going to be infinity. And then f of 3 is undefined. And it's undefined because at f of 3 we have that vertical asymptote. All right, so again, now that I did all three parts, I'm going to write my justification here. Since the limit as x approaches 3 of f of x does not equal f of 3, f of x is not continuous at x equals 3. All right, so for x equals 7, that way I don't make this video longer than it has to. I'm already, let me see, this is what, 13 minutes now? I'm gonna go ahead and put this as a try on your own, and you try to do the justification. Again, do these three things, and then at the end justify. And you have to follow this format for the AP exam. All right, so I'm gonna leave it at that. And okay, so for these next two problems, we want to determine whether each function is continuous or not, and if not continuous, justify your answer by using the definition of continuity. So again, most of you should probably recognize by now that if you have an expression in the denominator, and if I were to set this equal to 0, I know that I have an asymptote at x equals +3, right? Because +3 is what would get the denominator to be 0. So if I took the limit as x approaches 3 from the left. Now, again, I know we can say that there's an asymptote, so, you have some kind of discontinuity. But every time, if they want you to justify your answer, you have got to use those rules in mind for continuity. not rules, conditions, I'm sorry. So if I have the limit as x approaches 3 from the left of this expression for f of x, right? So again, I gotta go ahead and say, okay, well, what value can I use that's just to the left of 3? So I can go ahead and do, let's see, 1 divided by probably 2.999 minus 3. And what you'll notice is that it's pretty much going to be a negative big number. So if it's a negative big number, I'm just going to go ahead and say negative infinity. And if I were to do the limit as x approaches 3 coming from the right of f of x, well, I'm going to go ahead and pick a number just slightly above 3. So instead I'll do 3.001, and then I'll have a very big positive number instead. Okay? And you could also mention that f of 3 is undefined. So again, justifying our answer by using the definition of continuity, we went ahead and proved it over here, so we can say that f is not continuous at x equals 3, right? And I'll just put in parentheses, vertical asymptote. Okay. In this case over here, if I have g of x of 2x squared plus 7x plus 6, all divided by x plus 2, well, I know I can go ahead and start factoring this out. So if I were to factor this out, I have 2 sets of parentheses, and I know the 2 values for the first term would have to be 2x and x here. And let's see, I got to start thinking, what 2 numbers multiply to give me 6? Well, it can be like 1 and 6 or 2 and 3. Or 2 and 3, but then I have to figure out like if which combination of these numbers that if I put it in these blank spaces would ensure that I get the middle term to be 7x. Well, if I did plus 3 and plus 2, right? I know some of you don't really like the shortcut. Some of you want to do the long method of doing it. If you're comfortable doing that, go for it. I don't want to spend too much time on that. And then if I go ahead and rewrite the denominator, that's what I have, and I know that this will cancel out, and I'm just essentially left with 2x plus 3. So remember, if you were to factor out a rational expression and something canceled out, then you know you have a whole at x equals negative 2. All right, so let's see. Now, here's the thing. If I know that I have a whole at x equals negative 2, then I'm going to go ahead and like justify why it's discontinuous at that point. So first of all, I'm going to go ahead and double check the limit as x approaches negative 2. Let's do it from the left first and double check that. So if I do it from the left, this portion is going to be like if I plug in negative 2 into this, it's going to be negative 2 times 2 plus 3, right? And I'll end up with negative 4 plus 3, which is negative 1. All right. If I were to go ahead and do the limit as x approaches negative 2 from the right of g of x, well, again, I can just go ahead and plug in negative 2 into this, and then I get the same thing again. It'll be negative 1. But the problem is f of negative 2 is undefined, right? Because again, if I were to just plug in this function, what it would look like, it would almost look like a function. Oh, shoot. All right, sorry. If I were to graph this whole function, it would look like a function that, like a linear function with a y-intercept of 3 and a slope of 2. It would kind of look like that, except that x equals negative 2, there would be a hole, right? It's actually probably more down here because it's at negative 1, but you get the point. There would be a hole over here at x equals negative 2. So the limit as you approach negative 2 from the left and the right is going to arrive at the same place at negative 1. But the problem is f of negative 2 is undefined. So again, I know you can just say that you have a hole, but if they ever ask you to justify your answer, you have to show them the conditions that that we learned at the beginning of this section. So we know that G is not continuous. At x equals negative 2. And I'm just going to put in parentheses removable discontinuity, just so that we know why. Discontinuity. All right. So let's kind of move on to the next page. All right, so on the next page, this is a style of problem that I've seen quite a few times on the AP exam. They would say, use the definition of continuity to find the value of k so that the function is continuous for all real numbers. So here, obviously, we've got a piecewise function, and we want to ensure that it's going to be continuous throughout all of the different points. Well, if I look at this function, I know that like a quadratic equation is going to, or a quadratic function is going to be continuous. I know that a linear function is going to be continuous, but the question is, if I have them pieced together, I want to make sure that they're continuous at this point right here where they would most likely break off. All right? So really the best way of doing that is we're going to use our conditions that we know. If I look at the limit as x approaches 2 coming from the left, well, if it's coming from the left, I'm looking at this function ultimately, right? So that's what I'm going to be looking at of g of x, all right? And we know that this has to be the same thing as the limit as x approaches 2 from the right of g of x, all right? This has to be the case. So, and again, if it's coming from the right, then that's referring to this equation right here where x is greater than 2. So if I plugged in these formulas into this equation, then we know we're going to have the limit as x approaches 2 from the left of kx squared is equal to the limit as x approaches 2 from the right of kx minus 6, right? So here's the thing. If both of these sides have to be the same, when I plug in 2 into this and 2 into this, we got to figure out what value of k will let that happen. So when I plug in x into that, I should get k times 2 squared is equal to 2k minus 6. So this is essentially 4k is equal to 2k minus 6. I subtract 2k from both sides, and I get that. So k should be equal to negative 3. All right. So if I put in a value of k negative 3 into this, then if I were to plug in 2 into both of those, they would both be in the exact same place. All right. Similarly for this one, well, this one's a little bit tricky because we have an absolute value. So the question here is, if I took the limit as x approaches 4 from the left of h of x, and this is actually, you know what, this is a really good problem for me to go over because I don't think we've done too many absolute values. So that's the same thing as the limit as x approaches 4 from the left of the absolute value of x minus 4 over x minus 4. Well, here's the thing. If I just plugged in 4 directly, I would get 0 over 0, right? Absolute value of 0 divided by 0. So we know that we can't work with that. It's indeterminate. So here's the thing. If we're approaching 4 coming from the left, well, you can plug in a value less than that, but what some people, or a mistake that I imagine some people are going to do, is they're going to say, well, if I have x minus 4 on the top and x minus 4 on the bottom, let me find my sticky note or this. Some people might make the mistake of saying, well, if I have x minus 4 on the top and x minus 4 on the bottom, well, those cancel and I'm left with 1, right? That's not necessarily the case. Because if I'm taking the absolute value, well, let's see. If I were to get a value that's just less than 4, right? I would have running out of space here, but I would have 3.9, let's just say 3.99 minus 4 absolute value divided by 3.99 minus 4. One thing you'll notice is that at the top, right? If I did 3.99 minus 4, I'll end up with a negative number. Right? Now, but the thing is, if I'm taking the absolute value of that, it's going to turn positive. But the bottom is still going to stay negative. So if I have a positive version of the same number divided by a negative version of that same number, then it's going to end up being negative 1. Okay, so be really careful with absolute values. You need to understand intuitively and figure out which side, if it's coming from the left or the right, is it coming from. If it was coming from the right, then we could use like 4.01, and then it would still be positive on the top and the bottom, and it would be positive 1. So just kind of look out for those types of problems. So either way, so we took care of the limit of h of x as x approaches 4 from the left. We're also going to do the limit of x approaches 4 from the right of h of x, right? And we know that that's going to be equal to let's see, if I plugged in 4 into this function, I would get 5k minus 16. All right. So when I go ahead and I have to set these two equal to each other. So I have 5k minus 16 is equal to -1. I know I add 16 to the other side, so I have 5k is equal to 15. Divide by 5, k is equal to 3. And that's your answer for that. At this k value, we know that it's going to be continuous at x equals 4. So this problem down here is pretty involved. It's going to have 3 equations right here. So, I mean, let's just do it. So given h of x is all 3 of these functions, for what values of x is h of x not continuous? So this one isn't necessarily asking for a k value. They're just asking for you to verify if this is continuous at all. So, I mean, let's just kind of check it. Let's do the limit. So obviously the x value we're looking at is -2. So if I looked at the limit as x approaches -2 from the left, we're looking at this function right there, right? So we would go ahead and, so if h of x is going to be equal to, so if I plug in -2 into this, I get -2 times -2 minus 5 is equal to, that's positive 4 minus 5 is -1. If I did the limit as x approaches -2 from the right of h of x, right? So from the right, that's referring to this equation right there because it's obviously values greater than -2. If I plug that in, I'll get -2 cubed minus 6 times -2 plus 3. So when I go ahead and work that out, that's -8 plus 12 plus 3. Mental math. Wait, did I even do that right? So plus 12 plus 3, that is -1. All right. Now, if I were, did I do that right? That is -8. That is positive 12 plus 3. No. I'm sorry. -8 minus 12 is 4. 4 plus 3 is 7. Wow. Sorry about that. So anyway, and then if I were to look at h of -2, because again, that's one of the conditions, is that it has to be this has to be the same as these other two. So I can already tell you right now that it's not continuous, but just to kind of hit home, if I were to go ahead and define what is the definition of h of -2 is 3, right? None of the conditions have been met. So sorry, I had to edit something out because the wording was just done so poorly. So none of the conditions for continuity have been met. All right, now for the very last page of this section, I feel like these are 2 problems that I've pretty much gone over. So this is very similar to the very last one we did. And then this is one where I'm going to have you're going to have to do a system of equations for that one. So I'm curious to see if you guys can figure this one out on your own without my help. Of course, as per usual, I'm going to post the solutions, but hopefully this video was helpful. If not, just ask me any questions and I'll see what I can do to help. Take care.